This is video 5.1b as in boy in the section 5.1 on systems of equations in two variables. We're on page 440 dealing with applications. Where it says frequently the most challenging and time-consuming steps in the problem-solving process is translating a situation to mathematical language. In other words, taking a story problem and making an equation or equations out of it. So one of the things that we're going to do is learn how to make tables, like on page 440, and get familiar with these story problems in using two variables and systems of equations. So, example 6. We've got this caramel corn, and it's worth $2.50 a pound, and it's mixed with honey roasted mixed nuts, and the honey roasted mixed nuts are worth $7.50 a pound. Okay, so what we're going to do is we're going to mix those together, a $2.50 a pound and a $7.50 a pound, which means when we mix the two, we're going to get a price per pound of somewhere between the $2.50 and the $7.50. In fact, what they're interested in is mixing them together so that we get a 20-pound mixture worth $4.50 a pound. So we're going to have to put some of the caramel corn and some of the honey roasted mixed nuts together, make 20 pounds, and have it be worth $4.50 a pound. In order to do that, we want to know how much caramel corn and how many pounds of honey roasted mixed nuts are we going to have to add in order to do that. Okay, so let's look at what we've got here. I like to use these little tables here down at the bottom, so we're going to go skip a few things and go right down there to look at that. So we've got this table. It looks like this, and we have our caramel corn, and we have our nuts, and we have our mixture. Okay, so we're going to have three different columns there. Price per pound is going to be in our first row. Number of pounds, that's an LB for pounds, and then we're going to have the value of the mix down here. Okay, so what do we know about our caramel corn? Well, we know that the price per pound is $2.50. We know the price per pound of our nuts is $7.50, and we know that we're going to want a mixture that's worth $4.50 a pound. Okay? Now let's see number of pounds we have. We're trying to find out how much corn and how many pounds of our honey roasted mixed nuts we're going to need, so that when we add those two together, we get 20 pounds. And we know that the value of the mixture, or of the corn, is whatever the cost is times X. Okay, so when we take the amount of corn and mix it with the amount of nuts to get our mixture, we're going to end up with $4.50 a pound times 20, which let's go ahead and multiply these two so we know how much our mixture is going to be worth when we're all done. So if we take $4.50 a pound times 20, we're going to get $90 worth of mix when we're all done. Okay, and I know that when I take this amount and add them up, that's going to give me the $90. Okay, so I'm going to take price per pound times X to find out how much the value of the corn is going to be, the caramel corn. Then I'm going to take $7.50 times how many pounds of the mixed nuts I'm going to use to tell me the total value of the mixed nuts. So that when I add these two, I'm going to get my 90. So what do I know here? I know that if I take this amount right here, x plus y equals 20, if I take the number of pounds of caramel corn to the number of pounds of mixed nuts, I'm going to get 20 pounds. I also know that if I take $2.50 times how many pounds of caramel corn plus 750 times how many pounds of mixed nuts, I'm going to get $90 worth of mixed snack or whatever it is. Okay, so I have those two. So 250x plus 750y equals 90. Okay, so at this point I am done with everything there except just being able to use my system of equations to solve this. So I have a couple options here. I can use the substitution method, and I can say x equals 20 minus y, and then take 20 minus y and plug in here and solve it. Or I can use the elimination method. Now if I use the elimination method, I come up with a little bit of a problem here, and that problem is that I've got decimals here. So one of the things you start out doing right away is multiply all of this times 10. So we've got our top equation. I'm going to spread these out a little bit. And then I've got 25x plus 75y equals 900. Took away my decimals is all I did. And we can do that as long as we do everything to both sides of the equal sign. We're good to go. Now, let me make this look a little more like a 25. Now I can use elimination. I can multiply this whole thing by negative 25 so that it's the same as that one there, but opposite in sign. So that gives me negative 25x minus 25y equals negative 500. And then I've got 25x plus 75y equals 900. And I can add those go away. I end up with 50y equals 400. And my y then is equal to 8. And if my y equals 8, I can plug it back in the original problem up there at the top and find out that my x value is going to be 12. So that means that I can replace my x with 12 and my y with 8. So what should happen then is if I were to take 12 plus 8, I add those up and I get 20, true. 250 times 12 plus 750 times 8 gives me $90. So that means that my answer is going to be, I'm going to need 12 pounds of candy corn and 8 pounds of honey roasted mixed nuts in order to get a $90 solution that weighs 20 pounds. Okay? So next story problem, top of page 442, example 7, has to do with a boating. These whole boat in the river problems. Okay, so Carrie's motorboat takes 3 hours to make it downstream with a current of 3 miles per hour. The return trip against the same current takes 5 hours. Find the speed of the boat in still water. So going up the river, he's got the river pushing him back. Going down the river, we've got the river pushing him down. And we want to know, so that isn't really the inaccurate speed of how fast he's going in still water. So that's what we're going to look for here. So again, like using the table, they kind of wait on the table until later, but I like to use it early here. And we've got this, distance, rate, and time. So we have distance, rate, and time. So if you remember, you've got distance equals RT. So that's what we're going to look at here. So we've got distance, we have the rate, and we have the time. So we've got down and up. And what we're looking for again is how fast the boat is going in still water. We want the rate while the boat is in still water. Okay, do we know anything about the distance? 3 hours to make it downstream with a 3 mile an hour current. And the return trip against the same, we know nothing about distance. We have no idea how far Carrie took his fancy little motorboat and went upstream or downstream. Do we know how fast he went? Well, he went how fast he would go in still water when he went downstream. He went his rate, how fast he would go in still water, plus that 3 mile an hour that the current would be pushing him. So if he was going 20 mile an hour in still water, when he went downstream, that current would push him another 3 miles an hour, so he'd be going 23. So whatever his rate was plus 3. Now when he went upstream, whatever his rate was, it's going to be slowed down by 3 mile an hour because he's going against the current. So he's going to, whatever his rate is in still water, we're going to have to subtract 3 from it. So let's look at what else we know. The return trip against the current takes 5 hours. So the return trip took 5 when he went upstream. And it said it took him 3 hours to go downstream. Alright, so we filled in all of our blanks there. So if we look at this, downstream, D equals R plus 3 times 3. And upstream, his distance is R minus 3 times 5. So let's go ahead and do some manipulating as far as, well, one of the things I do know is that the distance he went downstream and the distance he went upstream are the same. It doesn't say that he went further downstream, because if he started at point A, let's say he started there and went downstream, he has to turn around and come back upstream. And why would he go further or not as far of a distance? He would go back to where he started from. So our distances are going to be the same in this. So if our distances are the same, then D equals D, which means this equals this. So I can write this as 3 times R plus 3, my first one, downstream, equals 5 times R minus 3. And if I do my distribution, I've got 3R plus 9 equals 5R minus 15. And I do the math and I find out that R equals 12. So that's how far he went in still water. There wasn't anything else we had to do. There weren't several variables there to solve. It was just solving for one variable. And the key thing here was just making these distances equal, which means you could make this equal to this, giving you one variable, one equation, and real quick and easy, able to go ahead and find out how fast he was going in still water. So that is it. We're going to skip example 8, and that should give you enough information to go ahead and start on 5.1 homework.